Okay, so this is capacitors and resonance. And so let's first talk about capacitors and capacitance itself. So capacitance is like if you take a bottle of something, how much does it contain? For example, if I take this bottle of spray cleaner or car wax, it tells how many fluid ounces it is. Or if you take a gallon milk jug, it will say gallon of milk. Okay, so that's the quantity of milk. So capacitance is the ability to store energy. And how it stores it is in electrostatic charge. And the capacitor is actually a device that's designed to store this electrical charge, just like a gallon jug of milk will hold a gallon of milk. So capacitors, the construction of a capacitor is using these two plates. You see this plate up here and this plate down here. So those are two metal plates, and then there's a layer in the middle that's called a dielectric material. Dielectric, if you just look at the word itself, it's dielectric, right? So that kills electricity per se. Yeah, essentially it's an insulating layer that separates these two plates. Obviously, if you didn't have this insulating layer, you'll just have one thick plate, right? That won't do anything. So by having this insulating layer, you separate these two plates. And these are the two terminals that will connect to it. So this terminal up here and this terminal down here. The symbols for capacitors are like this. Sometimes they'll also have two straight lines, but the proper way to do it is to have this like a curved line. Anytime you put a slash across it, that means it's a variable. And if they have a like a plus here, that it's a polarized capacitor. Normally these are polarized capacitors. This curved line is the negative side, the straight line is the plus side, just like what you can see here. So obviously if they don't indicate which is the negative line, it's assumed that this is the lower one is the negative line, if the upper one is the positive line. We talked about this. So if you have a circuit like this, you have a source voltage. So by the way, this is a DC source. And we have a switch and a capacitor like this. And you notice that the capacitor, the plus side is connected to the plus side, the minus side is connected to the minus side. So right now, across this capacitor, I have 0 volts. If I connect this circuit, close this switch, what will happen is all the free electrons on this positive terminal will travel to this positive terminal. They get attracted to this. And while we don't talk about the a different kind of charge, but you'll get this negative charge at this negative terminal here. Essentially, what this will do is it will pull all of the electrons out of, it will push all the electrons from here into here. It will push all the electrons from this negative terminal into here. In semiconductors, we talk about a different kind of charge. I was going to talk about it, but let's not do that and just confuse things. If you can think of it, you'll have the electrons, the negatively charged electrons pushed into this terminal. And also, as many electrons from here, it'll leave here, leaving this top part of net positive charge. So what will happen is you'll have this plus side and a negative side. And if you look at this, it's almost like a battery right now, right? So that's the two pictures that we looked at before this put together. Now, if you open this switch, so this is A, this is B, and this is C. If you open this switch, if you open that switch right here, what will happen is this positive charge will remain positive, this negative charge will remain negative, at least for a while, depending on the construction of the capacitor. And if you remove this device from this circuit like this, if you took this out, so this will act like a battery. I mean, for practical purposes, it would happen this way, but you can imagine if you put a light bulb across this device, if your light bulb would light up, you put that light bulb across this device, it will light up. Now, technically it's not going to because of the capacitance, the characteristics, but for all practical purposes, this voltage here will equal this voltage here. It won't be exactly the same, but it will be pretty close. So in this case, we are charging the capacitor. You see how it's going like this. So electrons will be pushed into here, electrons will be leaving here, like this. So we are charging this capacitor right now. It's like charging your cell phone, the battery in your cell phone. Okay. And if you turn the switch down here, what will happen is the capacitor will discharge. In other words, these electrons will travel from here across like this into here. Now, shorting a capacitor like this between these two terminals is not a very advisable thing to do. But what is shown between this A and B is that you can charge and discharge a capacitor. So, going back to that previous slide, one thing to remember is that before you handle any capacitors like this, these devices here, before a person handles this, or in a circuit, if you work with these devices, I'll show you a few later on, but you must make sure that you discharge it. So you can discharge it by just connecting a tool across the terminals. Not. Okay? You don't do that. If you do that, what will happen, if you put a tool across it, like let's say a metal screwdriver or a wrench handle or something like that, that's going to happen. And that's not pleasant. And if you put your fingers across that that metal thing was already there, somebody's going to get some serious burns or get a pretty nice electric shock. Here's another Einstein putting a screwdriver across it, and it's going to do that. And obviously, throughout my career, I've had a few of these things explode, and I don't think I've ever done one myself, but nevertheless, when they explode, these capacitors are filled with some kind of oil-like substance in here. And the stuff all spews out, and it's a fine mist of some carcinogenic oil that a person will have all over their body. So you don't want to put a tool across it, but you want to discharge the capacitor. The easiest way to do that is putting like a 1 mega ohm resistor, pretty hefty, couple of watt resistor. Again, depends on the voltage and the current of the capacitor. But a big heavy-duty resistor of like, when I say big, I mean the capacity or the resistance of it, so that you slowly discharge the capacitor. And what I have done is just usually if I'm working on a 12-volt system, I'll just put a 12-volt light bulb across it. So resonance is a characteristic of inductors and capacitors. We already talked about this one, X of L. It's inductive capacity, like that. Inductive reactance Okay, X of L, inductive reactance, this is capacitive reactance, X of C. So these two act actually like resistance. So the units of this is also ohms. Okay, X of L and X of C. So those act like resistors, but unlike regular, carbon combustion resistors or wire wound resistors, these are dependent on the frequency. Okay, and that's this F right here. We talked about this already. Inductive reactance, X of L is 2 pi constant, right? F is the frequency, L is the inductance. So for capacitors, it's the inverse 2 pi, F frequency is C capacitance. Remember we talked about something like this, where you have at Lambeau Field, you have 60,000 cell phones, and just one cell phone will ring. At the beginning of the semester, we had a slide, not this slide, but something similar to this, and saying, how does that happen? Happens because of the principle of resonance. So here we are talking about this microstrip patch antenna. That's the antenna that's used in like cellular phones or mobile phones. And it talks about resonance. And here's the citation for it. So all things have resonance, including our human bodies, even though it's not a mechanical structure, but it does have resonance. So it's like earthquake, the resonance, that's what makes the building collapse. So resonance frequency is where X of L is equal to X of C. Inductive reactance is equal to inductive capacitance. So at that point you will get the least impedance or the resistance. So this is impedance, or X is the resistance, you see on this y-axis, and this is as you increase the frequency. So X of L, the inductive reactance, it increases as you increase the frequency. X of C decreases as you increase frequency. If you decrease the frequency, X of C. X of C decreases as you increase the frequency. And you can see that from the curve, right? If you decrease the frequency or reduce the frequency, X of C goes up, but X of L goes down. You can see that from these two curves. So this is the minimum of both of them, or the crossing point of the two. And that's called the resonance frequency, F of R. And it's at that resonance frequency that you will get the maximum amplitude. So it's used in tuning applications. So the calculation for resonance frequency, F of R, is this formula, L being inductance, C being capacitance. Well, you can calculate these two also and get this, but it's easier to use this one. So we'll build a circuit using these devices, a 1 kilo ohm resistor, 1 microfarad capacitor, and a 47 millihenry inductor. So the first thing you need to do is to calculate the resonance frequency. So you have to use this formula. And it's just a case of putting the numbers into the formula. You should be pretty comfortable with this. So F of R, resonance frequency, inverse, just this one, 2 pi square root 47 times 10 to the minus third, which is this one, and times 1 times 10 to the minus 6. Oh, I've said hertz. That's wrong. It should be it shouldn't be hertz. It's got the capacitance value. Farads. It should be F here, not hertz. So make sure you make that correction. Okay. Or understand that this is wrong here. It's not hertz. We are trying to calculate the hertz, the frequency. So this should be farads. And this is henries, which is this one here. This one is this number. 1 micro farads right here. I'm doing that again. Okay. And so the resonance frequency is 734 hertz. Okay. Just make sure that you realize this number, this HZ is wrong. When I upload this, the PowerPoint, I'll make that correction. So what I'm asking is to do this circuit, build this circuit in multisim. I will build this circuit. I'll do it in another video because I need to get closer to the computer. I can't right now from where I'm recording this. And I want to know what is the voltage across the resistor, which is this one here. The voltage across the inductor, which is this one here. Voltage across the capacitor, which is this one here. And I also want to know, so what happens to these voltages when it's at resonance frequency? And then I also want to know what is, when I increase the frequency by 2, what happens? When I decrease the frequency by 2, what happens? Or divided by 2. What are your conclusions? And so I want you to upload to Canvas the table which is in the module, and the table in the module looks something like this. So that's the table. I don't know if you can see it, but that's the table. So it just asks what is the voltage across each of these devices and your conclusions. So for this particular one, I have already calculated the frequency to be 734. So the others you'll have to calculate the frequency. Alright, so I'm going to stop here and we'll go to building the circuit.